For millennia, humanity has looked to the night sky with wonder, charting the celestial dance of stars and planets. Our ancestors wove myths and legends around these distant lights, but their understanding was limited by the naked eye. The universe remained a vast, enigmatic tapestry, its deepest secrets hidden just beyond our perception, waiting for a revolutionary tool to unveil them. That tool arrived in the early 17th century, the telescope. Simple yet profound, this optical marvel extended human vision, piercing the veil of distance and revealing a universe far more complex and dynamic than ever imagined. It transformed astronomy from a descriptive art into a quantitative science, marking the dawn of a new era of cosmic discovery. Galileo Galilei quickly turned his rudimentary spyglass towards the heavens. What he saw shattered centuries of established cosmic understanding. The moon was not a perfect sphere, but mountainous. Jupiter possessed its own orbiting moons, and Venus exhibited phases like our moon, definitively disproving the geocentric model. These early observations, while groundbreaking, were just the beginning. The fundamental principle of the telescope, collecting and focusing light, would be refined over centuries, leading to increasingly powerful instruments that could gather fainter light from ever more distant cosmic objects. Each enhancement unlocked new layers of universal truth. Optical telescopes, which operate in the visible light spectrum, remain the bedrock of astronomy. They allow us to see what our eyes would perceive if only they were far more sensitive and larger. Today's giant ground-based optical telescopes, with their massive primary mirrors, collect millions of times more light than the human eye. These colossal instruments are strategically placed in remote, high-altitude desert locations, far from urban light pollution and atmospheric turbulence. Sites like Mauna Kea in Hawaii or the Atacama Desert in Chile offer the crisp, dry air necessary for observing the universe with minimal distortion. The Earth's atmosphere, while vital for life, is a challenge for optical astronomers. It blurs starlight through a phenomenon known as seeing. To overcome this, modern observatories employ adaptive optics, systems that rapidly adjust the telescope's mirror to counteract atmospheric distortions, effectively sharpening astronomical images in real time. Adaptive optics often rely on guide stars, either natural bright stars or artificial ones created by powerful lasers projected into the upper atmosphere. By precisely measuring how these guide stars twinkle, the system can calculate and correct the atmospheric blurring across the entire field of view. Beyond the visible light our eyes perceive, the universe emits radiation across the entire electromagnetic spectrum, from long radio waves to incredibly short gamma rays. Each segment of this spectrum reveals different cosmic phenomena, from the coolest gas clouds to the hottest, most energetic explosions. Radio telescopes are designed to detect the longest wavelengths, invisible to optical instruments. They capture signals from incredibly cold, distant objects, allowing astronomers to map gas, dust, and magnetic fields in galaxies, and even trace the remnants of the universe's fiery birth. Unlike optical telescopes, which need perfectly smooth mirrors, radio dishes can be built with larger tolerances because the wavelengths they detect are much longer. This allows them to be immense, sometimes hundreds of meters across, offering incredible collecting area for faint signals. By linking multiple radio dishes separated by vast distances, a technique called interferometry dramatically increases their effective resolution. This allows astronomers to achieve image sharpness equivalent to a single telescope thousands of kilometers wide, revealing fine details in distant radio sources. Infrared telescopes detect heat radiation, allowing us to peer through thick clouds of cosmic dust that obscure visible light. This is crucial for studying star formation within dusty nebulae and observing the atmospheres of distant exoplanets before their light reaches us. While some infrared observations can be made from high-altitude ground-based observatories, atmospheric water vapor strongly absorbs infrared light. For a clear view, space-based infrared telescopes, cooled to extremely low temperatures, are essential to avoid their own heat interfering with sensitive measurements. The Spitzer Space Telescope, for instance, revolutionized our understanding of star and planet formation by unveiling hidden nurseries within dense dust clouds. Its observations showed countless infant stars and protoplanetary disks, mapping the very beginnings of new solar systems. Moving to shorter wavelengths, ultraviolet telescopes observe phenomena emitting highly energetic light, such as young, hot stars, active galactic nuclei, and the vast halos of gas surrounding galaxies. Earth's ozone layer completely blocks most ultraviolet radiation, necessitating space-based observatories. The Hubble Space Telescope, perhaps the most iconic, has contributed immensely to ultraviolet astronomy. Its observations have traced the distribution of hot gas in galactic interactions, shed light on the conditions in the early universe, and even characterized the composition of distant quasars. X-ray telescopes capture even higher energy radiation. This is the domain of extreme cosmic phenomena, black holes actively consuming matter, superheated gas in galaxy clusters, and the remnants of colossal stellar explosions. Such observations require mirrors that are polished to an almost impossible smoothness. X-ray mirrors don't reflect light head-on like optical mirrors. Instead, they operate on a grazing incidence principle, where X-rays barely skim the polished surfaces at shallow angles, much like skipping a stone across water. This allows them to funnel and focus the incredibly energetic X-rays. The Chandra X-ray Observatory is a prime example, providing unparalleled views of X-ray sources. It has revealed the shockwaves from supernova explosions, mapped the distribution of dark matter in galaxy clusters through their X-ray emitting gas, and precisely located accreting black holes. At the very highest energies are gamma-ray telescopes. These instruments detect the most violent and energetic events in the cosmos, like gamma-ray bursts, the most powerful explosions in the universe, and the extreme jets emanating from active galactic nuclei. Gamma rays are so energetic that they cannot be focused by mirrors. Instead, gamma-ray telescopes often work by detecting the cascade of particles created when a gamma-ray photon interacts with a detector material. These high-energy events release crucial clues about their origins. The Fermi Gamma-ray Space Telescope, for example, has catalogued thousands of gamma-ray sources, from pulsars spinning hundreds of times a second to distant blazars whose supermassive black holes are blasting jets of particles directly at us, offering vital insights into cosmic accelerators. Telescopes don't just reveal light, they've expanded our senses far beyond. Neutrino observatories, for instance, detect ghostly particles that pass almost unimpeded through matter, offering a unique window into stellar interiors, supernovae, and the universe's most extreme environments. Gravitational wave detectors, like LIGO and Virgo, are a radically different kind of telescope. They don't use light at all. Instead, they measure tiny ripples in spacetime itself, caused by cataclysmic events like the merger of black holes or neutron stars, opening the era of multi-messenger astronomy. With this incredible arsenal of observational tools, astronomers have begun to truly decode the cosmos piece by piece. Our solar system, once a realm of pure speculation, has been meticulously mapped, its planets and moons revealing complex geological histories and tantalizing hints of past or present life. Optical telescopes, from ground and space, have provided breathtaking close-ups of planetary surfaces. The towering volcanoes of Mars, the shattered terrain of our moon, and the active geysers of outer solar system moons. These images unveil worlds unique and alien, yet governed by familiar physical laws. Infrared observations of gas giants like Jupiter and Saturn have allowed us to peer beneath their opaque cloud layers, revealing dynamic atmospheric currents, giant storms, and the complex chemistry occurring deep within these colossal worlds. Radio telescopes have mapped the surfaces of Venus and Titan, worlds perpetually shrouded by thick atmospheres, one incredibly hot, the other incredibly cold. These radar images reveal mountains, plains, and even liquid methane lakes, completely hidden from visible light. Moving beyond our cosmic backyard, telescopes have taught us about the birthplace, life, and death of stars. Optical observations show vast nebulae where hydrogen gas collapses under gravity, forming dense protostars that ignite into brilliant stellar furnaces. As stars age, space telescopes reveal their evolution through various stages. The calm stability of main-sequence stars like our Sun, the expansion into red giants, and finally, the dramatic expulsion of outer layers to form planetary nebulae. The violent end stages of massive stars are observed across multiple wavelengths. Optical telescopes capture the initial flash of supernovae, while X-ray and radio telescopes reveal the rapidly expanding remnants, glowing with the energy of the explosion and the dense neutron stars or black holes left behind. One of the most profound discoveries attributed to telescopes is the existence of exoplanets, planets orbiting stars other than our Sun. While we cannot directly see most of them, telescopes detect their subtle gravitational tugs on their stars or the faint dimming of starlight as they transit. The Kepler Space Telescope, in particular, was a prolific planet hunter, using the transit method to discover thousands of exoplanet candidates. Its continuous, high-precision monitoring of a single patch of sky revolutionized our understanding of planetary systems beyond our own. Future telescopes, like the James Webb Space Telescope, are designed to characterize exoplanet atmospheres by analyzing the chemical fingerprints in the starlight that passes through them. This pursuit seeks the elusive signatures of life, such as oxygen or methane. Beyond individual stars and planets, telescopes have meticulously mapped the structure of our own Milky Way galaxy. Radio observations reveal its spiral arms, traced by glowing clouds of hydrogen and vast molecular clouds, providing a cosmic cartography of our galactic home. Optical telescopes pierce through the galactic plane's dust to resolve individual stars and clusters, revealing the Milky Way's composition and dynamics. We can see ancient globular clusters orbiting the halo and vibrant open clusters within the disk, each with their own story. At the heart of our galaxy lies a supermassive black hole, Sagittarius A. While invisible directly, X-ray and radio telescopes observe the orbits of stars incredibly close to it, tracing their frantic dance and confirming the immense gravitational pull of this cosmic behemoth. Looking further out, telescopes reveal the universe teeming with other galaxies, each a sprawling island of billions of stars. Optical images showcase their incredible diversity, from majestic spirals with elegant arms to chaotic, active irregulars and featureless, ancient ellipticals. The Hubble Deep Field observations, accomplished primarily with optical light, captured faint galaxies billions of light-years away, looking back in time to the early universe. This single patch of sky revealed thousands of galaxies, each a tiny beacon from cosmology's infancy. Galaxy mergers and interactions, observed across multiple wavelengths, are critical to galaxy evolution. Optical images show distorted shapes and tidal tails, while radio and X-ray data reveal gas flows, shockwaves, and bursts of star formation triggered by these cosmic collisions. Some galaxies harbor intensely luminous, active galactic nuclei, powered by supermassive black holes accreting vast amounts of matter. X-ray and gamma-ray telescopes are essential for studying these phenomena, which can outshine their entire host galaxy. Moving beyond individual objects, telescopes have unveiled the large-scale structure of the universe. Galaxies are not randomly distributed, but form vast filaments and clusters, separated by enormous voids resembling a colossal cosmic web. The most profound secret revealed by telescopes is the expanding universe. Edwin Hubble, using optical observations of distant galaxies, noted a systematic redshift in their light. The further away a galaxy was, the faster it appeared to be receding from us. This Hubble's law, as it became known, provided the first strong observational evidence for the Big Bang theory, a moment of cosmic genesis when the entire universe began from an incredibly hot, dense state and has been expanding ever since. The afterglow of the Big Bang, the cosmic microwave background, CMB, is another triumph for radio and microwave telescopes. This faint, uniform radiation fills the entire universe, a relic from about 380,000 years after creation, when the universe cooled enough for light to travel freely. COBE, WMAP, and Planck space telescopes accurately mapped these tiny temperature fluctuations in the CMB, providing a baby picture of the universe. These subtle variations are the seeds from which all future structures, stars, galaxies, clusters, would eventually grow. Telescopes also provide indirect evidence for the universe's most enigmatic components, dark matter and dark energy. We cannot see them directly, but their gravitational influence is observed through the bending of light and the accelerating expansion of space. The missing mass in galaxy clusters, inferred from X-ray observations of hot gas and gravitational lensing, points to dark matter. This mysterious substance makes up about a quarter of the universe's mass, providing the gravitational scaffolding for galaxies to form. The accelerating expansion of the universe, discovered through highly precise observations of distant supernovae with optical telescopes, points to dark energy. This pervasive force seems to be driving galaxies apart at an ever-increasing rate, a profound mystery that challenges our understanding of physics. Black holes, once theoretical curiosities, are now firmly established cosmic entities thanks to multi-wavelength observations. X-ray telescopes detect the searing hot gas swirling into them, while radio telescopes image their powerful jets and even their event horizons. The Event Horizon Telescope, a global network of radio dishes, recently captured the first direct image of a black hole's shadow, a dark void against the glowing backdrop of its accretion disk. This monumental achievement visually confirmed what theory predicted. Beyond imaging, spectroscopic observations using all types of telescopes reveal the chemical composition, temperature, density, and motion of cosmic objects. By splitting light into its constituent wavelengths, astronomers read the universe's chemical fingerprints. The Doppler effect, observed in the shift of spectral lines towards red receding or blue approaching, allows us to measure the velocities of galaxies, stars, and gas clouds. This is how we know the universe is expanding and galaxies are rotating. Astronomical spectroscopy has identified the abundance of elements in stars and gas clouds, confirming that all elements heavier than hydrogen and helium were forged in the hearts of stars and dispersed through supernova explosions, enriching the cosmos for future generations of stars and planets. The very latest technological advancements continue to push the boundaries of what telescopes can achieve. Segmented mirrors allow for the construction of truly colossal light-gathering surfaces that would be impossible to build as a single piece, reaching diameters of 30 meters or more. Liquid mirror telescopes, which use a spinning pool of liquid mercury or gallium to form a parabolic reflecting surface, offer an innovative and cost-effective approach to creating extremely large, perfectly smooth mirrors for certain types of astronomical surveys. Beyond simply larger apertures, distributed observatories utilizing very long baseline interferometry, VLBI, combine data from telescopes across continents, dramatically increasing resolution. The Event Horizon Telescope is a prime example of this global collaboration. Space telescopes, free from atmospheric distortion, remain indispensable. The upcoming James Webb Space Telescope, poised to revolutionize infrared astronomy, will peer back further in time than ever before, revealing the universe's very first galaxies and stars. Webb's unprecedented sensitivity and infrared capabilities will allow us to observe objects whose light has been redshifted so much by the universe's expansion that it now falls outside the visible spectrum. This means seeing the faint glow of protogalaxies. Even more ambitious are concepts for future space observatories. Missions like Habitable Exoplanet Observatory, HABEX, or Large Ultraviolet Optical Infrared Surveyor, LUVOIR, are envisioned to directly image Earth-like exoplanets and search for biosignatures. The next generation of ground-based, extremely large telescopes, ELTs, with mirrors tens of meters across, like the European Extremely Large Telescope, EELT, or the 30-meter telescope, TMT, will provide unparalleled detail for studying exoplanet atmospheres and distant galaxies. The future of astronomy is also multi-messenger astronomy, combining observations from different cosmic messengers to understand a single event. This involves correlating light, gravitational waves, and neutrinos to gain a complete picture of extreme cosmic phenomena. For example, the first observed merger of two neutron stars triggered both a gravitational wave signal and a subsequent electromagnetic flash, observed by optical, X-ray, and radio telescopes. This event confirmed the origin of heavy elements like gold and platinum. The ongoing search for extraterrestrial life is perhaps the ultimate quest driven by our telescopes. From characterizing exoplanet atmospheres to exploring subsurface oceans on icy moons like Europa, these instruments are our frontline in answering humanity's oldest question: are we alone? The ability of telescopes to penetrate the veil of cosmic dust and gas has allowed us to map the entire life cycle of stars, from their birth in dense molecular clouds to their dramatic deaths as supernovae or silent collapses into black holes. This provides a coherent narrative for our own sun's past and future. Infrared observations are uniquely suited for studying the coldest, densest regions of space where stars begin to form. These regions, cloaked in dust, would be invisible to optical telescopes, but the heat radiated by collapsing gas clouds shines brightly in infrared. As protostars gather more mass, they become T-Tauri stars, characterized by powerful outflows and jets of gas visible in both optical and infrared. These powerful jets clear away surrounding material, preparing the nascent star for sustained nuclear fusion. Optical telescopes reveal open star clusters, groupings of hundreds or thousands of young, gravitationally unbound stars born from the same cosmic nursery. These clusters are often bright blue due to their numerous hot, massive, short-lived stars. The vast majority of a star's life is spent on the main sequence, stably fusing hydrogen into helium in its core. Optical and spectroscopic analyses of millions of stars across the sky reveal the incredible longevity of this phase, like our sun's expected 10 billion-year lifespan. When a star like our sun exhausts its core hydrogen fuel, it expands dramatically to become a red giant. Telescopes reveal these bloated, cooler, reddish stars, sometimes so large they would engulf the inner planets of our solar system. For low to medium mass stars, the outer layers are gently expelled, forming beautiful, expanding shells of gas called planetary nebulae. Optical telescopes capture their exquisite, often intricate shapes, glowing brilliantly from the ionizing radiation of the exposed core. The core of a planetary nebula contracts to become a white dwarf, a superdense remnant roughly the size of Earth. These are primarily observed by optical telescopes as faint, incredibly hot, compact stars that slowly cool over billions of years. Massive stars end their lives in spectacular supernova explosions. Optical telescopes detect the initial, incredibly bright flash, often outshining an entire galaxy for a few weeks, signaling the cataclysmic collapse of the stellar core. X-ray and radio telescopes then follow the evolution of the supernova remnant, an expanding bubble of gas, shocked by the explosion and radiating across the spectrum. These remnants are cosmic factories, dispersing newly forged heavy elements throughout the interstellar medium. At the heart of some supernova remnants lies an incredibly dense neutron star, formed from the collapsed core of a massive star. These rapidly rotating objects, called pulsars, emit beams of radio waves that sweep across Earth like a cosmic lighthouse, detected by radio telescopes. If the collapsing core is even more massive, it forms a black hole, an object so dense that nothing, not even light, can escape its gravitational pull. Telescopes can only observe black holes indirectly through their influence on surrounding matter. High-energy X-ray telescopes are crucial for detecting stellar mass black holes in binary systems. As matter from a companion star falls into the black hole, it heats to millions of degrees, emitting intense X-rays before crossing the event horizon. Large ground-based optical telescopes and space telescopes have been instrumental in the search for transiting exoplanets. The tiny, periodic dimming of a star's light as a planet passes in front of it is a measurable signature, even from vast distances. Beyond transits, the radial velocity method, using stellar spectroscopy, detects the subtle wobble of a star caused by the gravitational tug of an orbiting planet. This allows astronomers to infer a planet's mass and orbital period. Direct imaging of exoplanets is exceptionally challenging due to the overwhelming brightness of their host stars. However, advanced optical techniques and space telescopes, like the James Webb Space Telescope with its coronagraph, are making this a reality for larger, more distant planets. Studying exoplanet atmospheres through transmission spectroscopy is a frontier of exoplanet research. As starlight passes through the exoplanet's atmosphere during a transit, certain wavelengths are absorbed, revealing the chemical composition of its air. The potential for biosignatures, chemical indicators of life like oxygen, methane, or ozone, observed in exoplanet atmospheres, is the holy grail. Telescopes are being designed with this specific capability in mind, focusing on Earth-sized planets in habitable zones. The study of galaxies has been revolutionized by telescopes. From the early island universes, observed by distant fuzzes, to the present-day detailed structures, we've classified them by morphology and understood their evolutionary pathways. Spiral galaxies, like our Milky Way, are characterized by their rotating disks of stars, gas, and dust, organized into prominent spiral arms. Optical telescopes beautifully capture their intricate structure, often rich in blue star-forming regions. Elliptical galaxies are vast, spheroidal collections of older stars, with little active star formation or gas. Optical telescopes show them as smooth, often reddish, cosmic blobs, ranging from nearly spherical to highly elongated shapes. Irregular galaxies lack a distinct regular shape, often resulting from gravitational interactions or violent internal processes. They are often sites of intense star formation and are well observed in both optical and radio wavelengths. Galaxy mergers are catastrophic events driven by gravity, observed across all wavelengths. Optical images show the distortion and tidal tails, X-ray reveals superheated gas, and radio shows the ongoing star formation and gas flows from the collision. Quasars, the extremely luminous cores of active galaxies during the early universe, are powered by rapidly accreting supermassive black holes. Their incredible brightness, detected across the spectrum, allows us to study the universe when it was much younger. The most fundamental pillar of modern cosmology derived from telescope observations is the expanding universe. From Hubble's meticulous measurements of galactic redshifts to the cosmic microwave background, the evidence for a universe that began in a hot, dense state and has been expanding ever since is overwhelming. The cosmic microwave background, CMB radiation, a faint glow pervasive throughout the universe, is the oldest light we can ever hope to observe directly. It is the echo of the Big Bang, revealed by incredibly sensitive microwave telescopes like WMAP and Planck. These minute temperature variations in the CMB, observed with exquisite precision by space telescopes, are not random. They represent the initial density fluctuations, tiny seeds of structure, that eventually grew into the galaxies, clusters, and filaments we observe today. The analysis of these CMB anisotropies has allowed cosmologists to precisely determine the age of the universe, its geometry, and the relative proportions of ordinary matter, and dark energy, providing a standard model for cosmology. Dark matter, an invisible substance that interacts primarily through gravity, was inferred from telescopic observations of galaxy rotation curves and gravitational lensing. Galaxies and clusters possess far more mass than their visible matter accounts for. X-ray observations of galaxy clusters also provide compelling evidence for dark matter. The superheated gas between galaxies in a cluster requires a massive gravitational field to hold it in place, far exceeding that of the visible galaxies alone. Dark energy, arguably the most perplexing discovery, was revealed by optical telescopes observing distant type Ia supernovae. These standard candles showed that the universe's expansion is not slowing down due to gravity, but accelerating. The nature of dark energy remains one of the greatest mysteries in science, a uniform, pervasive force seemingly present everywhere in space, pushing galaxies apart. Telescopes provide the observational data points that challenge and inspire theoretical physicists. Black holes, from stellar mass to supermassive, are confirmed cosmic phenomena, primarily through multi-wavelength observations by dedicated X-ray and radio telescopes. They reveal the most extreme gravitational environments in the universe. The first ever image of a black hole, specifically its shadow against the superheated gas around it, was a landmark achievement by the Event Horizon Telescope, an Earth-sized radio interferometer. It combined data from numerous dishes globally to achieve unprecedented resolution. Stellar mass black holes are often found in binary systems where they pull matter from a companion star. As this gas spirals inwards, it heats to millions of degrees, producing a torrent of X-rays detected by orbiting observatories like Chandra and XMM Newton. The jets emanating from active galactic nuclei, powered by supermassive black holes, are incredible cosmic phenomena. Radio telescopes map these vast, relativistic outflows, sometimes extending for millions of light years, transporting immense energy across galactic scales. Spectroscopic analysis, a cornerstone of astrophysics enabled by telescopes, allows us to break down light into its constituent colors, revealing emission and absorption lines unique to each element. This chemical fingerprinting tells us what distant stars and galaxies are made of. This powerful technique also reveals the temperature, pressure, and density of cosmic gases by analyzing the width and intensity of spectral lines. It's like taking the universe's temperature and pressure gauges, all from billions of miles away. The Doppler effect is also measured through spectroscopy. A shift of spectral lines towards the blue end indicates an object is moving towards us, while a shift towards the red end means it's receding. This is how we know galaxies are streaming away from each other. Through the Doppler shift, telescopes trace galactic rotation curves, discovering the existence of dark matter by showing that stars in the outer regions of galaxies orbit much faster than the visible matter within their radius would suggest. Technological leaps have been central to every major astronomical discovery. Active and adaptive optics represent a profound advancement, continually deforming telescope mirrors to compensate for atmospheric blurring, turning fuzzy images into crisp, detailed views. Segmented mirrors, like those on the Keck telescopes or the upcoming ELTs, allow the construction of vast primary mirrors that would be impossible to cast as a single piece. Each segment is precisely aligned to act as a single, enormous optical surface. Interferometry, linking multiple distant telescopes optically or electronically, dramatically enhances resolution, making a distributed array of smaller telescopes equivalent to a single, gigantic telescope with a diameter spanning the distance between them. Space telescopes, free from the turbulent and opaque atmosphere, provide unparalleled clarity and access to otherwise blocked wavelengths. Hubble, Spitzer, Chandra, and the upcoming James Webb are testament to their invaluable contribution. The James Webb Space Telescope, specifically designed for infrared observations, is a monumental leap. Its massive, gold-coated beryllium mirror and intricate sunshield will allow it to detect the faint, highly redshifted light from the very first galaxies. Webb's ability to peer through cosmic dust clouds previously impenetrable to optical telescopes will revolutionize our understanding of star and planet formation, uncovering hidden nurseries across the Milky Way and beyond. The science of data processing and computing has become as crucial as the telescopes themselves. Handling petabytes of data, advanced algorithms are used to clean, combine, and analyze observations, extracting subtle signals from cosmic noise. Looking ahead, the next generation of ground-based, extremely large telescopes, ELTs, will boast primary mirrors ranging from 20 to nearly 40 meters in diameter, collecting unprecedented amounts of light to probe the most distant and faintest objects. These ELTs, equipped with advanced adaptive optics, will directly image more exoplanets and analyze their atmospheres for biosignatures, taking a significant step in the search for life beyond Earth by directly characterizing other worlds. The future also holds multi-messenger astronomy as a standard mode of observation. Telescopes across the entire electromagnetic spectrum will work in concert with gravitational wave observatories and neutrino detectors to completely capture extreme cosmic events. Events like merging black holes and neutron stars, observed by gravitational wave detectors, will immediately trigger follow-up observations by conventional telescopes, leading to a richer, more complete understanding of these incredibly energetic phenomena. The quest for life beyond Earth, ever present in humanity's imagination, is now firmly within the grasp of scientific exploration, driven by our ever-improving telescopes. From Mars rovers to exoplanet surveys, the tools are continually refined. The study of icy moons in our solar system, like Europa and Enceladus, by space probes equipped with specialized instruments, is a proxy for how we might one day search for life on larger exoplanets. Their subsurface oceans are prime targets. Telescopes continue to decode the cosmos, revealing its vastness, complexity, and dynamic nature. From the subatomic processes within stars to the grand evolution of galaxies, our instruments bring the universe into sharper focus, challenging our assumptions. Each new discovery, each sharper image, each novel detection method pushes the boundaries of human knowledge, reminding us of both the profound beauty and the immense mysteries that still await us in the cosmic tapestry. The journey of cosmic decoding is far from over. With every new generation of telescopes and observers, humanity's understanding of its place in the universe deepens, nurturing our curiosity and inspiring future generations to look up and wonder. Our relentless pursuit of cosmic understanding began with the simple act of looking up. Now, bolstered by incredible technology, we extend our senses across light years, interpreting whispers of ancient light and echoes of cosmic cataclysms. From the precise measurements of stellar distances using parallax with space telescopes to the mapping of dark matter halos with gravitational lensing, telescopes have built the very foundations of modern stellar and galactic astrophysics. The discovery of quasars, initially puzzling radio sources, revolutionized our view of active galaxies and their evolution. They highlighted the importance of supermassive black holes in shaping galactic environments in the early universe. Studying gamma-ray bursts, the most powerful explosions in the universe, requires swift, coordinated observations from telescopes across the globe and in space. These brief, intense flashes signal the birth of black holes or neutron star mergers. Pulsars, often observed by radio telescopes, are cosmic lighthouses, rapidly spinning neutron stars emitting beams of radiation that sweep across Earth. Their incredible timing precision rivals atomic clocks, making them unique cosmic laboratories for fundamental physics. The detection of extrasolar comets and asteroids directly passing through our solar system from interstellar space illustrates the evolving capabilities of telescopic surveys. These detections hint at the vast exchange of material between star systems. Understanding the formation and evolution of galaxy clusters, the largest gravitationally bound structures in the universe, relies heavily on X-ray observations of their superheated gas, which reveals their total mass and dynamic interactions. The universe's first light, the cosmic microwave background, is not just a uniform glow. Its tiny anisotropies, mapped with stunning precision by telescopes like Planck, are the seeds of all cosmic structure, telling us about ripples in spacetime during the universe's infancy. Searching for gravitational waves from incredibly distant, powerful cosmic events has opened an entirely new window onto the universe. LIGO and Virgo's listening for spacetime ripples allows us to probe phenomena that are invisible even to light. The future of astronomy involves even larger ground-based telescopes, equipped with adaptive optics that use many thousands of tiny actuators to perfect mirror shapes. These will achieve resolutions approaching those of space telescopes from Earth. Space-based interferometers, such as potential missions to directly image exoplanets, are visionary concepts that could one day create virtual telescopes spanning millions of kilometers, providing unprecedented detail and potentially revealing traces of alien biospheres. The continuous development of detector technology, from highly sensitive CCDs to superconducting nanowire arrays, further enhances telescope capabilities, capturing more photons and resolving fainter signals from the universe. Ultimately, telescopes are not just instruments. They are extensions of human curiosity, allowing us to connect with the cosmos in ways our ancestors could only dream. They are our eyes on the universe, continually decoding its profound and awe-inspiring secrets.